In this video, we're going to nudge our way into some multivariate modeling principles. Thus far, the relationships we've explored via visualization and statistical modeling have been bivariate, with one response variable y and one predictor x. For example, we've modeled bike ridership by quantitative predictors, such as wind speed and temperature. And we've modeled bike ridership by categorical predictors, such as weekend status and season. Each of these individual predictors tells us something about ridership. We see that it tends to be lower on windy days, higher on warm days, lower on weekends, and lower during the winter. Thus, if each one of these predictors tell us something about ridership, then perhaps using more than one of these predictors at a time would even better explain why ridership varies from day to day. So here's our goal. Our goal is to start exploring multivariate visualizations and models of relationships between some response variable y and multiple predictors, which we'll label as x1, x2, up to xp. The subscripts here just help us distinguish one predictor from the next. In exploring multivariate relationships, there's not going to be a singular rulebook or recipe to follow. Instead, we're going to be like master chefs. As you know, master chefs typically don't rely on the crutch of a cookbook. Nor does a cookbook exist that could include every possible rule for every possible dish that somebody would want to make. Rather, master chefs master the fundamentals of cooking, such as taste, texture, and aroma, and they master the ability to combine these fundamentals in new ways. Similarly, we'll seek to master some guiding principles in multivariate modeling. These principles will support a deeper understanding of the material, are better for long-term retention, and enhance our ability to generalize to new situations. That is, our ability to really apply what we learn in this course beyond this course itself. So not only are principles important, they're necessary. A rule book does not exist for modeling. So to explore these guiding principles, we're going to start with a few illustrative but not exhaustive scenarios. To begin, suppose we've explored the relationship between ridership and quantitative wind speed, and we wish to incorporate the categorical weekend status variable into this analysis. A powerful first step is visualizing the relationship between these three variables. To that end, I encourage you to pause your video and reflect on the following. How can we tweak this scatterplot here of ridership versus wind speed to also incorporate information about weekend status? In thinking about this question, remember that weekend status is categorical, with either true or false categories. Now there's more than one approach and one answer here, but the general principle is this. Just as we discussed when plotting ridership versus weekend status alone, visualizing a categorical variable requires some sort of mechanism for pulling apart or indicating the category groups. For example, we might use color, symbols, or even different plots or facets per group. Thus, one grouping strategy that we can take here is to color the scatterplot points of ridership versus wind speed according to their weekend status. Now we have information about all three variables on one plot. Picking it apart, there appears to be still a weak negative association between ridership and wind speed on both weekdays and weekends. Further, ridership tends to be lower on weekends no matter the wind speed. That is, we see that the blue dots for weekends tend to be below the red dots for weekdays. These same principles for visualizing the relationship between these three variables extend to building a statistical model of the trend in this relationship. Recall here that the model of ridership versus wind speed alone was described by a single line. I encourage you to pause here to reflect on the following. How might this model of ridership versus wind speed change when we incorporate the weekend predictor? That is, what do you think the new model will look like, or how might we draw this model on the scatter plot at right here? To answer this question, recall that when we modeled ridership by weekend status alone, we essentially got one model outcome for the two different category groups. So an understanding of typical ridership on weekends and weekdays, just two numbers. The same principle applies here. Incorporating weekend status into our model of ridership versus wind speed results in one model outcome or equation per group. Or visually, it pulls apart the singular model line into one model line per group. These two lines pick up on the two category trends in the scatter plot. On both weekends and weekdays, we see a negative association between ridership and wind speed. That is, both of the lines here have a negative slope. Further, ridership tends to be lower on weekends, no matter the wind speed. That is, the weekend line is below the weekday line. So in this first scenario, we've looked at incorporating one quantitative and one categorical predictor. Consider another scenario, two categorical predictors. For example, suppose we wish to model ridership by two categorical predictors, here season and weekend status. Starting with the relationship between ridership and season alone, we can visually incorporate information about weekend status using the usual mechanism. We can represent our weekend group information or category information by pulling apart our season information for each season for both weekend groups. In this case, this means that we pull apart each season's box plot into two, one for weekends and one for weekdays. This powerful visualization now illustrates the multivariate relationship in our three variables. We see that on both weekends and weekdays, ridership tends to be lower in the winter. Further, no matter the season, ridership tends to be higher on weekdays than weekends. We see that that's true in winter, summer, spring, and in fall. Next, in modeling the relationship between a response variable and a categorical predictor, recall that we get one model outcome per category. Thus, when modeling ridership by season alone over here, we'd have four possible model outcomes, which describe the typical ridership in each of the four seasons. By adding this second weekend categorical predictor, we now have 8 total category groups, weekends and weekdays in each of the four seasons. Thus, our model now has 8 possible outcomes, one per each category combination. Finally, let's move on from using two categorical predictors to two quantitative predictors. Suppose we've explored the relationship between ridership and the quantitative wind speed predictor, and we wish to incorporate the quantitative temperature into our analysis. Again, I encourage you to pause your video and reflect on the following. How can we tweak the scatterplot here of ridership versus wind speed to incorporate information about the quantitative temperature predictor? As always, there are several approaches and answers, but the general principle is this. Visualizing a quantitative variable requires an extra axis or numerical scale. Now, this is where visualizations get pretty tough. Visualizing anything beyond 2 dimensions, so 2 quantitative dimensions, is tough for the human brain, but we're going to try. For example, we might visualize the quantitative temperature information by scaling the size of our dots accordingly. But I think you would agree with me when I say that this plot in particular isn't very easy to read or understand, thus not very useful. Instead, we might visualize the quantitative temperature information using a color scale. This is a little easier to read. Mainly, the lighter plots correspond to warmer temperatures and darker plots correspond to cooler temperatures. Now, seeing that we have most of our lighter dots at the top left of the plot indicates that ridership tends to be higher on days, both with low wind speeds and warmer temperatures. Finally, we might visualize the quantitative temperature information by actually trying to give it its own axis. Now, though this 3D scatter plot is still tough to visually interpret, especially because we can't interact with it and rotate it, it is more in the spirit of the relationship here. Each day in our dataset has a coordinate defined by quantitative information on our three variables, or our three dimensions: ridership, wind speed, and temperature. Unfortunately, the difficulty of interpreting these visualizations isn't unique to this particular example. As our explorations expand to relationships between more and more variables, visualizing relationships is going to get even tougher. This is where statistical models are especially helpful. They can provide insights into relationships, even when those relationships are too complicated to visualize. With that, recall that the model of ridership versus wind speed alone is described by a single line. I encourage you to pause here to reflect on the following. How might this relationship, or the model of ridership versus wind speed, change if we incorporated a temperature predictor? For example, if you're looking at this plot at right, how might we draw the model? What might the model look like? Just as visualizing an extra quantitative variable increases the numerical scales or dimensions of our visualization, it also increases the physical dimensions of our model. Here, that means that our model expands from a singular line to an infinite plane. And this plane cuts through the cloud of our data points. For example, this plane captures the fact that at any temperature, ridership tends to decrease with wind speed. Further, at any wind speed, ridership tends to increase with temperature. Again, the goal of this video and our upcoming work in general has been to establish some multivariate principles. Relying on rules and memorization just isn't going to work in statistical modeling. A key theme in these principles has been to be mindful of what type of information we're working with, that is, whether our variables are quantitative or categorical. Even this simple distinction gets us pretty far in understanding how to explore multivariate relationships. For example, in visualizing relationships, our examples have reiterated that categorical variables require some sort of grouping mechanism, such as colors or symbols, and quantitative variables require an extra axis or numerical scale. In modeling relationships, our examples have reiterated that a categorical predictor requires a separate model equation for each group, and a quantitative predictor increases the physical dimensions of the model formula. For example, our model might go from a two-dimensional line to a three-dimensional plane. These principles will help with the next critical step of our multivariate analysis, not only being able to build and visualize a model, but being able to interpret the results.